Okay, so we're looking at topic 10 circles and beginning with 10-1 arcs and sectors. Start with a little bit of vocabulary here. So by now you all should know what a circle is. Here's your proper definition for it all. Set of points in a plane that are a fixed distance from the center. Right? Every circle has a center, and that point is equidistant, the same distance from any point on the circle itself. When we're speaking of circles, the circle itself is, that is this, and then you have your center in the middle. All right, radius again. It's like some of these terms, these first two terms you should already be familiar with. The radius, any segment with one endpoint on the circle and the other endpoint at the center of the circle, right? So segment DE is a radius, since point D is the center and E is a point on the circle. So it's a radius. Now if we take the radius and extend it to reach the other side, well then that makes it a diameter. Remember, since the center is equidistant from any point on the circle, all radii are congruent, always. All radii, now plural for radius is radii, so all the radii are congruent. Diameter is the same. Any diameter that passes through a circle will be congruent to any other diameter. Doesn't matter. Before I continue, you may have noticed up here, you have the symbol for a circle, and then the center is how we name the circle. That's why this one pictured here is circle A, and this one pictured over here is called circle D. If we look at the last example down here, this is circle P. The center point is the point used to name the circle. All right. So this is definitely, it should be a new concept, central angle. So remember, the central angle whose vertex is the center of the circle, right? So if we take any two radii, right, any two radii will form a central angle. Now, okay, so there you have it, central angle right here, APB, BPA, whatever you want to call it, but that's a central angle because the vertex is the center. Okay, so central angles are formed by radii, and I guess in some cases you can think of by diameters, mainly radii though. Okay. So moving on. So this section deals with arcs and sectors, and we'll get into that a little bit more. But the arc is central to this lesson here. So what is an arc? Well, it's a part of a circle that lies between 2 points on the circle, right? If I take any points on the circle, for example, A and B, the curve between them, the piece of the circle that connects those 2 points, that's an arc. Okay, so we name them just like we name segments. We use those 2 points, and we have a little arc symbol, which is just a curvy little line above it. Right? Arcs are measured in degrees, just like angles. And now arcs also have length, because remember, circles have circumference, so they have a distance around. So I guess we can say that arcs are measured 2 different ways. There's a degree measure, and there's a length measurement. So the way we distinguish them is by arc measure and arc length. If I say arc measure, I'm talking about the degree measurement. How many degrees does this arc span? Okay, so another way, so looking at the second bullet here. So another way to that, so the arcs can be formed simply by 2 points. You connect them on the curve, and that's it. But if you have radii, like here you have AP, so you have radius AP and radius BP. So since those two are radii, well, the points A and B together form the arc. And you can also have arcs created by lines and rays. It's pretty much any points. So something else to keep in mind regarding arcs, we have the segment addition postulate, so we actually can do something like that with arcs as well. Right? Arcs can be added together. Okay, so for example, we have this arc AB, and then we have the rest of the arc, or the rest of the circle around it. So if we add those two together, that gives us 360 degrees because circles are made up of 360 degrees. So let's talk about the difference between the two types of arcs, minor and major. Okay, so arc AB is a minor arc. As you can see, the central angle is 95 degrees. So arc AB is 95 degrees. Since it is less than 180 but greater than 0, that makes it a minor arc. Okay, and I already mentioned that second bullet here. Measure of a minor arc is equal to the measure of its central angle. Okay, so the central angle and the arc measure will always be the same. So you can use one to find the other and vice versa. The major arc, well, that's at the other end. Kind of one way to think about it is angles that are acute and obtuse in a sense. Acute angles are less than 90 but greater than 0, while obtuse angles are greater than 90 less than 180. This is kind of like that. Minor arcs are greater than 0 less than 180. Major arcs are greater than 180 less than 360. Okay, so that's how you can tell them apart. Another way to tell them apart is through the names. Okay, arc measures, minor arcs use 2 letters, major arcs use 3 letters. Why is this? Well, because if we just use AB, if minor and major arcs were named the same way, how could you tell the difference? If I say AB, arc measure AB, am I talking about AB like this, or AB the other way around? So we can't have the same naming method for both. It doesn't, it would cause confusion. So for major arcs, they use 3 letters, and the name, the arc, follows the letter order. So see, notice the arc is called ACB. So that means we begin at point A, follow the circle around till we get to point C, and then from C we complete the path at B. If you go ABC, well then that's a totally different arc. It's not the same thing as ACB. Order is important, just like the angle is called APB because we go from A to the vertex P and then to the point B. So A, vertex P, B. Got to follow that order. Now for this example, I'm going ahead and using, showing you how arcs can be, added together and such, or subtracted for that matter. You can do both. So since we know that arc measure AB is 95 degrees, well, I can take that away from 360 and that gives me the rest of it, which would be arc ACB. So arc ACB is 265 degrees. Okay, so let's go ahead and look at some examples over here. Let's start with the first one. So the first part, we're looking for the arc CD. That's this one right here. It's a pretty easy one to solve for because, well, we have the central angle related to it, CAD, right? Notice that the arc and the central angle share the letters. If we take away the A, CD, CD. Now, that's something to keep in mind. And then it's also very important to make sure not to mistake CAD with, with a major arc. Be very careful to follow the points where they are. That's a mistake that frequently happens. Students will mistake major arcs for central angles. Anyway, so we know that CAD is 51 degrees, as was previously mentioned. The measure of the central angle is the same as the measure of the central arc, so it's measure CAD equals measure CD. So by transitive property, we know that CD must equal 51. And there we go, that's it. Some of these are pretty easy, some of them require a little bit more work. Now example 2, CFD. Remember, have to follow the points in order. We can't go from C to D, that doesn't make sense. Where's F? Down all the way over here. So I'll go from C Go all the way around to F, and then keep going until I return to point D. So we want to know what is the measurement of all this over here. Now you can see, oh, well, it's broken up into all these little pieces. So you might think, oh, well, I need to use all of these little pieces. I got to figure them all out. No. Remember, you want to look at the figure carefully, break it down. What's helping me, what's not. So if you notice, CFD, you can see, follow the curve, go to point F, work our way back around to point D. CFD covers everything except what? Except this 51, except for that central angle, except for arc CD, which we just determined. CFD is everything else. So how many degrees do we have total? 360. Every circle is made up of 360 degrees. So all we need to do is take 360, subtract C8, that central angle. And I'm using angle CAD since that's the given one, but really what we were talking about is arc CD here. Essentially they're interchangeable. And there we go, so 309. Pretty simple. And some of them will require a little bit more work, but it's in general you're adding and subtracting. That's pretty much all that this lesson requires. So I think these two examples here pretty much cover it. Let's see. And then we have all these different examples. Some of them are straightforward, like example 1. You should already have all the answers for these, but you definitely still want to look at them and break them down to see what, how they differ. And for example, okay, this one's, or look for arc LK. Well, we see that one's already given, so pretty easy. That one's done. Now let's look at this one, number 2, UWV. And we're starting UWV. So it's made up of all this. It's made up of these two arcs that are given. Well, we have the central angles, right? But since this is 140, that means the arc from U to W, that's an arc measure of 140. From W to V is an arc measure of 160, so we simply add them together. And there we have it. Let's look at QRS. QRS, that one, no, not number 3. That one's just like number 2. Let's see. EF is one that would require subtraction. Now with these questions, what you want to do is take segments that look like diameters, assume for them to be diameters. Alright, I forgot to put that in the directions here, but that's something you want to do. I believe it's in the directions of the assignment. That's something you want to do here. If it looks like a diameter, assume it is a diameter. For example, LJ is a diameter, EG is a diameter, HG is a diameter. Can't really do that for 2, 3, and 4. But anyway, since we're looking for EF, well, if this is a diameter, what does a diameter do to a circle? Cuts it right down the middle. Diameters cut circles in half. If you take any one diameter, that is. So we know that if this is what we're looking for, but EF and FG together make a semicircle, so 180 minus 110, oops, 70 degrees. Let's see, this last one, HIJ. Well, if we assume this is a diameter from H to I to J, we don't even have to do any math there. 180. Little common sense. Let's see. I think that pretty much covers this section, so let's move on to the next portion. Arc length. Again, arc length and arc measure, not the same thing. And arc measure refers to the degree measurement of the arc. How many degrees out of the 360 is covered between these 2 points. Arc length, that refers to the actual distance, feet, meters, miles, etc. So the arc length is a piece of the circumference, right? That's a piece of the circumference. So the distance along an arc measured in linear units. Okay. So we have the formula right here, 2 pi r multiplied by m over 360. Notice I mentioned the word circumference, 2 pi r. Isn't that the formula for circumference? If we ignore the m over 360, the m divided by 360, this gives us this piece by itself, a 2 pi r. That's the whole circumference, right? So that's important to note to understand why this formula works the way that it does. Right? The reason that we multiply m over 360 to 2 pi r, the purpose of this fraction is because, remember, an arc is a fraction of the circumference. It's a percentage. So the question is, what percentage? Well, the arc you're looking for represents a certain number of degrees out of the total 360. Okay, so that's why we multiply by this fraction here, m over 360. So let's look at what these variables stand for. Pretty straightforward. L, that's the length of the arc. R is your radius, and m is one of two things. It's either the central angle or the arc measure itself. All right, but it has to be in degrees. Okay, and here we'll be using 3.14, keep things simple as far as pi goes. 3.14 is what we're going to be using for pi. So let's look at these examples down here. Well, we got to make sure we put everything in the right place, right? So let's see. Example 2 and part 1 over here. What do we know? So the radius is 10 feet. Pi is 3.14. We've already covered that over here. And the measurement of the arc is 90 degrees. So if we were to connect point C and point D to the center to create the two radii, we would have a central angle of 90 degrees. All right, so we have everything we need. Now we just substitute into we can go to our formula. Substituting into the formula, we get 2 times 3.14 times 10 times 90 over 360. So working that out, multiplying 2 times 3.14 times 10, we get 62.8. Let me see, got my calculator here. You should get you'll get an answer to the hundredths. Actually, no, not in this case. But anyway, for the most part in these examples, I'm rounding to the nearest tenth, at each step of the way. Now, if you don't do that, your answer will vary just a little bit, but ultimately you'll be able to identify the correct answer when you get to the end of the question sheet related to these problems. You shouldn't be off by more than a decimal place here and there. You should be able to easily pick out, if you're doing everything right when it comes to the question sheets, you'll be able to pick out the correct solution each and every time. Now, rounding is one of those tricky things, So anyway, 2 times 3.14 times 10 rounds to 62.8. 90 over 360 can be reduced to 1/4. So now we just multiply 62 by 1/4. Well, that's essentially 62.8 divided by 4. So we get that the arc, if we were to take the arc and stretch it out flat like a string, it'd be 15.7. And that's essentially what circumference is. If you take a circle and you flatten it out, you stretch it out so that it's a straight line, that's where your circumference comes from. All right, the second one is a word problem. There's no picture, but you don't really need much of a picture. Everything's spelled out for you. There's only 2 examples here in the notes. All the other ones have pictures to go along with them. I'm trying to give you that visual aid. So anyway, we're told arc with a measure of 35 degrees in a circle with radius of 3 inches. It's really easy to pinpoint everything, right? The radius is 3 inches. The arc measure is 35 degrees, and pi is always 3.14, or the whole long crazy decimal. So these problems are all going to be mostly the same. It's just a matter of substituting everything in the right place. So doing that here, we know what our formula is. So it becomes 2 times 3.14 times 3 times 35 over 360. Notice the similarities. The only difference is the length of the radius and the angle measurement. That's it. Everything works out the same. So 2 times 3.14 times 3 gives us 18.8. Rounded, rounded. 35 over 360 reduces to 7 over 72. Multiplying 18.8 times 7 over 72, we get 131.6 divided by 72. Finally, we divide by the 131. 131.6 is 18.8 times 7 divided by 72, and we get 1.8 inches. Okay, so a small distance here, but regardless, so we get. Okay, let's see. Yeah, so then same process, just different numbers. Literally the only thing that's different. In each case, you're rounding to the nearest tenth, using 3.14 for pi. And it's just, well, there's my arc measure, m. Here's my radius, 6. So spelled out pretty clearly. Some more examples, plenty of examples to practice with. You have all the solutions already on the PDF notes. Just a matter of sitting down and working it out. Again, depending on when you're rounding and how you're rounding, the answer may change a little bit, but it shouldn't change so drastically if you're plugging everything properly and evaluating it properly. Let's move on to the last bit here, sector area. So sector area, well, it's an area, so it's kind of like, I like to think of this in terms of pizza slices. That's what it looks like. So, like how much, how big is the pizza slice? What's the area of this piece? Right here, this orange, slice. I don't want to call it a triangle because they're not triangles. So again, since we're talking about area, notice the formula features the area of the circle, pi r squared. If we cover up, if we ignore the m over 360, pi r squared is the formula for the area as a whole of the whole thing. And again, we're looking for a fraction of the area, which is why this m over 360 comes into play. How many degrees m of all 360 of the full circle are shared here. That's the purpose of that m over 360. Nothing changes, except I guess instead of L, we're now using A. A is the area, R is the radius, and M is the measure of the central angle or arc measure. Either one works. Let's have a look. And well, identifying our variables. The radius is 3 inches in length. Then you can always tell them apart because the arc measure M is in degrees, and the radius will be in a unit. It will be a unit of length: inches, feet, meters, so on and so forth. So 3 inches, pi is 3.14, and the arc measure is 80 degrees. So we substitute into our formula: 3.14 times 3 squared times 80 over 360. So 3 squared is 9. 80 over 360 reduces to 2/9. Multiply here. 3.14 times 9 gives us 28.3. And once we simplify, 28.3 times 2 over 9, 56.6 over 9. And then finally we divide that fraction. We get 6. We round it, gets rounded to 6.3. So take a moment to absorb that, review that example. Plugging and evaluating. Pretty straightforward. Now what about this next one? So, reasonably similar, isn't it? Only thing that's changed, instead of the arc measure, they gave you the central angle. In either case, that's your m. The radius is now 6 centimeters instead of 3 inches. So overall, there's really no difference except for the change in the values. It's the great thing about these formulas. Just change the numbers. But if you know where each piece goes and how to work with it, you can work it out. Like a puzzle, you have the pieces. If you just know how to put them together, then all puzzles. We're talking about jigsaw puzzles. That is, they all work the same way. You find the pieces that go together. You begin with the corners, so on and so forth. Right, but there's a process to each of them. If you can do one, you should be able to figure out another jigsaw puzzle. It's the same thing here. If you understand where the pieces go in the formula, plug them in and evaluate. Pretty straightforward. So substituting. Pi 3.14, the radius is 6. And the central angle, or arc measure, 120. 6 squared is 36. 120 over 360 reduces to 1/3. 3.14 times 36 is 113. Multiplying by 1/3 is the same as dividing by 3, so you should get 37.7. You have to round, but that's what you end up with. And all the steps are here and everything, but you should try to do even these two examples. Try them on your own, just to make sure that you understand. Just to make sure that you also can get 37.7 on your own. If you don't want to do those, well, you have plenty of examples over here. Okay, plenty of examples to work with and try out. You have the answer already, but remember, it's not a question of, oh, the answer's there. The question is, can you get the answer yourself? Can you get from point A to point B? Again, I like to use a map as a reference. If I pull up a map and say, well, I can show you where, the state, I can show you where Washington State is, that doesn't mean I know how to get there. We have the convenience of Google Maps, but imagine you didn't have Google Maps. What do? You need to find your way from point A to point B. What roads do you take? What highways? That's not the idea here. The idea with any problem. It's like, okay, I know what I have, I know what I'm looking for, but can I bridge the two pieces? Okay, so that pretty much wraps up this lesson. We just have plenty of examples here. It's a little tough to tell. It should have been 30 degrees around here somewhere. Yeah, this well, that's 30 degrees in this middle. Hold on, let me go back and figure this out in case there's any others. Now it looks like it's just in that last slide. This one right here. It's a little tough to see, but it's supposed to be a 30. Could have sworn I put a little 30 in here somewhere. Oh, anyway, well, that wraps up this lesson. So I hope you found it useful. If not, message me and we can sort out some of these examples.